Welcome. Let's name some acids. To name acids, you need to figure out something about the anion involved in your acid. Acid formulas will generally have H in front for the H pluses, the protons, and it'll have some sort of anion. If an acid were to dissociate, dissolve in water, it would give you a proton and an anion. So it's this anion that is going to let us know what our acid is going to be named. So let's go over this template. So if your anion ends in "ide," like with chloride, you're going to use this template. You're going to put a hydro in the front. The blank is for the element or anion name. And then in the back, you're going to put ic acid. So we have chloride, hydrochloric acid, hydrochloric acid. If your anion ends in "ite," like the polyatomic anion nitrite, there's no hydro in front. You have a blank for the name, like nitrite. But that "ite" ending, you're going to change it to "us." Okay, so reviewing, "ide" became "ic" here. "Ite" becomes "us," so this would be nitrous acid. And then with this last one, we have something similar to nitrite, but we have nitrate. So "ate" becomes "ic." We have nitric acid. All right, and that's our template. I had a student teach me something funny a while back, and it helped her memorize the acid names effectively. I like this, and I still teach this to this day. I don't remember the name of the student, but thank you, whoever you were. And what she found or made up, I don't remember, but this is what she said. My ride has hydrolics instead of hydraulics, hydrolics. So if your anion ends in "ide," put a hydro in the front and an "ic" in the back. If your anion ends in "ite," then change it to an "us." So Sprite is delicious. And then lastly, I ate something icky. If you have "ate," then change it to an "ic." Notice with "ate," there's no hydro in front. It's just going to end in "ic." Whereas if it's "ide," you put a hydro in front and an "ic" in the back. That hydro is important so that it can distinguish these two acids. All right, so let's go through an example with iodine. We're going to name 5 different acids here. Make sure I'm on the screen. Okay, good. And so 4 of the 5 acids feature polyatomic anions, and 1 features a normal monoatomic anion. So what I did in these pictures is I gave Lewis structures for each of these acids. You don't have to do this, but I like to always show, when appropriate, an atom-to-atom sort of picture of what's going on. So here are our acids. Let's take this top one, for example, HiO4. And then this aqueous symbol, it's technically not an acid until it's dissolved into water. You don't use the acid naming until you're actually in water. So that's why you see the AQ, aqueous symbols everywhere. All right, so this acid, we dissolve into water. This H comes off as a H+, and it leaves its electron behind so that this anion ends up with a minus. IO4- we know as the periodate anion, IO4-. IO4-, you go to your polyatomic ion list and you'll realize, oh, that is periodate. So to name this acid, we change the 8 into ic acid. So this would be periodic acid. All right, my common dad joke for this acid is that it's the periodic table's favorite acid because periodic is the same spelling as periodic. All right, let's keep going. Here we have HiO3, And upon dissociation, we see that this right here is an IO3 minus anion called the iodate anion. 8 becomes ick, and then we add an acid. Same thing that we did up there. So this would be iodic acid. All right, remove another oxygen, we get iodite. And if you have the ending of ite, you get us. So us acid. So iodous acid. All right, remove another oxygen, we get the hypoiodite anion. Ite ending, Sprite is delicious, right? So we get OUS acid. So this will be hypoiodous acid. I didn't add the prefix hypo here. That was already a part of the name for the polyatomic anion, hypoiodite. Okay, and I can keep writing the chemical formulas. This was IO4 minus, IO3 minus. This is IO2 minus, iodite. This was an IO minus, hypoiodite. Finally here we have a monoatomic, meaning a single atom anion, the iodide anion. So we're not, we don't have polyatomic ion endings anymore of 8 or ite. It's ide, and if you have an ide in the back, you have to put a hydro in the front. This is the only time we add a prefix to the front, and this is hydroiodic acid. Don't put iodous acid because, again, the rule is if it ends in ide, you have to end it with an ick. All right? Even if there's no oxygens and you're tempted to use the us, that is used for lower amounts of oxygen in your acid. That's just not the way the naming rules go. Okay, ide, you have to put hydro in front and ick in the back. So this would be hydroiodic acid. Notice the name sounds very similar to iodic acid. In fact, if I took away the hydro, it would be exactly iodic acid. But we can see that these are two different chemical formulas, and therefore they need unique names for each acid. Okay, so that was some examples, and just kind of as a closing thought here, here are the typical acids that, looking at my and other instructors, other books, Chem 101, Intro Chem curriculums, these are some acids I see very commonly in those curriculums or textbooks. Give or take maybe a few acids, and I know for many of these acids, these are encountered in a Chem 101 sort of laboratory. Even some of these are kind of used quite often in upper levels of chemistry as well. Particularly hydrochloric acid is used a lot in the chem lab, nitric acid, phosphoric, sulfuric definitely. And acetic acid, also known as vinegar, but acetate, ate becomes ick, acetic acid. The ones I had named in red, those are what we call strong acids. The strong acids I put in red. In strong acids, the name is a little bit misleading, but strong acids, the definition of a strong acid is 100% dissociation. So something like hydrochloric acid, very common, strong acid. When you dissolve it into water, you have an H plus ion grabbed off of the chloride by a nearby water molecule, and then the chloride is left on its own. So you have that full like separation when it dissolves. Whereas these other acids in blue, they're called weak acids because when you dissolve them into water, there's very little to no dissociation. So a weaker acid, let's do, I don't know, carbonic acid. If we were to dissociate, write the dissociation for carbonic acid, it would look like that. But if you were to measure the amount of ionization in solution, like the conductivity, the more ions you have in solution, the less, or excuse me, the more ions you have in solution, the more you'll conduct electricity in solution. Something like carbonic acid wouldn't conduct too much electricity, which means this doesn't really happen too much, this dissociation. Strong versus weak acids. This would be a weak acid in blue. Strong versus weak is, in chemical terms, only representing how much you dissociate. That doesn't mean that it's like not an acid or something like that. You know, if I had a very concentrated solution of acetic acid, vinegar, you know, if I were to stick my hand in it, it'd probably hurt. You know, if I were to get in my eyes, I think I'd do some major damage. So don't mistake quote unquote weakness with not being able to do chemistry. That's usually not the case at all. It's just only talking about how things look like when they dissolve into water. That's it. Okay, so what's the take-home message? Apply the naming rules so that you can name any acid, or admittedly, some students, they say, hey, this is enough of a list where I can just drill this into my head and memorize it. I'll leave that up to you to decide. Thanks for watching and have a great day. Take care.